The definite integral is the basis for half of the work in calculus and therefore requires a significant amount of attention. When one studies the integral, one also learns about antiderivatives. Hi, my name is Tom Atwater, and let's start today's lesson by looking at some properties of the definite integral. Rules for definite integrals. The order of integration. What this tells us is if you switch the order of the limits, then you just get the negative of the integral. The zero property simply says if you integrate it from a to a, in other words, you have the same upper as lower limit, then you get 0 as the value of the integral. The constant multiple rule tells us if you're multiplying the function by a constant, then all you need to do is multiply the integral by that same constant for any constant value. The sum and difference tells us that the integral of the sum of two individual functions is equal to the sum of the individual integrals. And the same thing with the difference. The difference, or the integral of the difference of two functions is simply the individual integrals being subtracted. Okay, let's take a look now at what's called the additivity property. And that tells us that if we're taking an integral from a to b, and then right beside that picking up at b and going on to c, so in other words, we're really taking side-by-side pieces, that you can simply combine that and say that's one integral that goes all the way from a to c. The max-min inequality tells us that basically over here, the minimum value for the function over that entire integral is obviously the smallest that the integral itself can ever be. And that if you take the maximum value of f over that whole integral, that's the greatest value that the integral will ever be. And finally, the domination property tells us that if we have two functions and one of them is bigger than the other, then when you take their integrals, the same one is still bigger than the other one. And if you have a function which is positive, then you will get an integral which is positive. Okay, that's a lot of properties. So let's try an example where we apply some of these properties. Let's find the following integrals based on the fact that we have one integral from 1 to 2 of f of x dx, and that equals 5. So let's take a look at number 1. We're taking an integral from 1 to 2, which is the same as what we had in the original. The fact that the variable is different simply means we're giving it a new name, but it's still the same integral, and so this is equal to 5. In problem number 2, we have the same bounds, and this time what we're doing is multiplying by a constant, the square root of 3. And we know that when you multiply the function by a constant, you simply multiply the integral itself, which is 5, by that constant. In example 3, notice that we have reversed the limits. Instead of 1 to 2, we're going from 2 to 1, and you'll remember that that just said to us that it's the negative of the integral. In number 4, we're multiplying the integral by -1. I'm sorry, you're multiplying the function by -1. We have the same limits as the original one, so therefore, if you're multiplying the function by 1, you simply multiply the integral by a -1, and you get -5. So that's 4 examples of using some of those properties. Now we can use the definite integrals to find the average value of a function. Let's see how we would do that in terms of finding the average value. The average, and in which case we're talking about the mean as opposed to the median or the mode averages, the mean value. The definition is if f is an integrable function on the closed interval ab, its average, again the mean value on that closed interval, is given by the average of f equals 1 over b minus a times the integral from a to b of f of x dx. Let's look at an example of where we will apply this formula of finding the average. We're going to use a calculator that can integrate to find the average value of the function on the interval. At what points in the interval does the function assume its average value? The function we're going to deal with is y equals negative 3x squared minus 1 over the interval 0, 1. What I want to show you is how you would do this on your calculator. Because your graphing calculator, your TI-83 plus or your TI-84 plus, has a function which allows you to plug in and find the integral. And it's located by hitting the math key and then the 9 key. And on a TI-84, it's going to come up with f int. However, on your TI-83 plus, you will see instead that it will come up with n int. Both of those require 4 arguments, and you can see them here. It requires the function, which is negative 3x squared minus 1. It requires the variable over which we are integrating, which is x, and then the lower bound followed by the upper bound. So 4 different arguments that you plug in. And once you hit enter, you get the value of that integral, which in this case for negative 3x squared minus 1 over the interval from 0 to 1 is equal to negative 2. The other part of this question said, at what point does the function assume that average value? So let's work that out right now. We know that the average value is negative 2. And we want to know when does it assume that value. In other words, we need to solve the problem. Negative 2 is equal to negative 3x squared minus 1. What that leaves me with, of course, is that 1 is equal to 3x squared. X squared is equal to 1/3. And when I take the square root, I get x equals 1 over the square root of 3, and I get x equals negative 1 over the square root of 3. But we can't use the negative because the interval, remember, was from 0 to 1. So the negative 1 over radical 3 is not included. And what that means is that the function assumes its average value when x is equal to 1 over radical 3. And that average value that it assumes is negative 2. Finding the point at which a function takes on its average value is an example of that mean value theorem for integrals, which states that over the interval of integration, there is at least one point at which the function takes on the average value. Now, let's look at a connection between differential and integral calculus. If f is any antiderivative, if capital F is any antiderivative of lowercase f, then we have the integral from a to x of f of t dt is equal to capital F of x plus c. And that leads to setting x equal to a, changes the integral so that the lower and upper bounds are both a, and that we're evaluating when x equals a, so we plug in a in for x on this side, and notice what happens. Remember, the zero theorem tells us if the upper and lower bounds are the same, then the integral has a value of 0. On the right-hand side, we've left it the same, but what that means is that the constant c has the value negative capital F of a. And what we can do now is substitute that back in to the equation on the previous screen, and we come up with this equation, which tells us that the integral from a to x of f of t dt is equal to capital F of x minus capital F of a. All right, let's try some examples and apply this particular theorem. Evaluate the following integrals using antiderivatives. And we have 3 examples: the integration from pi to 2 pi of sine x dx. Then we have, for number 2, the integral from 1 to 4 of 2x dx. And number 3, the integral from negative 1 to 1 of 1 over 1 plus x squared dx. I'm going to move to a screen that will give me a little bit more room, and we'll do each one of these. So the integral from pi to 2 pi of sine x dx. We have to think about what particular function has a derivative that equals sine x. And you should immediately think, ooh, cosine x. And just remember that the derivative of cosine is negative sine, and therefore we have to use as the antiderivative negative cosine, because then we will get, when we take the derivative of negative cosine, we'll get negative of negative sine, which is positive sine. So this would be equal to that negative cosine of 2 pi minus negative cosine of pi. And when we evaluate that, we will get an answer, negative 1 minus 1 equals negative 2. Let's move on to number 2. We want to find a function that when we take its derivative will be 2x. And so when you think about that, x squared, if we differentiate x squared, that's 2x. So this function is going to be equal to x squared, which means we evaluate 4 squared minus 1 squared. And of course, we know that that simplifies to 15. And finally, on number 3, we have the integral from negative 1 to 1 of 1 over 1 plus x squared. This one you may have to really think hard about, but it's the formula for arctangent. That is tan inverse. So this one is equal to tan inverse, or again, arctan of the upper bound 1 minus arctan of the lower bound negative 1. And when you evaluate that, each of these, well, the first one is pi over 4, then it's minus a negative pi over 4. And so we get pi over 2 as the value of that integral. All right, that was great, but now it's time for you to try a problem. I would like you to evaluate the integral using antiderivatives for the following integral. From 1 to e, integrate 1 over x dx. Pause the video while you work on this problem, and when you're finished, restart the video so you can check your solution. Welcome back. Let's see how you did on this problem. We have to think about what function, when we differentiate it, will give us 1 over x. And yes, that's the natural log of x function. So this, I'm going to move it over a little bit to give me more room. But the integral from 1 to e of 1 over x dx is going to be the natural log of e minus the natural log of 1. Remember, the natural or the log of 1, regardless of the base, is always 0. And again, that's because any base raised to the power 0 gives us 1. So this is 0. And then the natural log of e is base e, right? So log base e of e is 1. So it's 1 minus 0, and the integral has the value, when you evaluate it, of being equal to 1. Let's now combine the following or the preceding procedures with everything we've learned into the average value formula. So what we're going to do is find the average value of the function on the interval using antiderivatives to compute the integral. The function we have is y equals secant squared x over the interval from 0 to pi over 4. And so we want the average value, and that means that we're going to use the formula for the average value of f. And remember, that formula is 1 over b minus a times the integral from a to b of f of x dx. And in this particular case, then, we have that the average be 1 over, and remember, b is pi over 4, a is 0. The integral that we're taking from 0 to pi over 4 of secant squared x dx. And remember that the function whose derivative is secant squared x, that is, if we take a function and take its derivative, we get secant squared x, that's tangent of x. So we need to evaluate, so the antiderivative of the secant squared x is tan x. So this part simplifies to 4 over pi. Then the rest of this, I'll put in parentheses because we're going to have the tangent of pi over 4 minus the tangent of 0. And now, the tangent of pi over 4 is 1. The tangent of 0 is 0. 1 minus 0, of course, is 1. So our answer is 4 over pi. And that's what you get for the average value of that function. So there were some great applications of using the antiderivative. In this lesson, we learned the properties of the definite integrals, and we learned how to use applications of those properties. Now, be sure to work the exercises that your teacher assigns, and we'll see you next time.